So let's start today with a review question that we covered in Wednesday's lecture. I've got a chemical reaction here. Water and ammonia creating ammonium hydroxide. Which one of those three is the acid? Anyone still working? Okay. Let's take a look at what we said. Oh, we're not sure. Well, let's kind of go through this piece by piece then. Someone here, who said water? All right, Michael, why is it water? Okay, so we're looking for hydrogen. Can anyone anyone here say ammonia and H3? All right, no one's willing to admit it. I can respect that. All right, so none of you should have said this last one. The reason why you shouldn't have said the last one at all is because it's got two things going against it. First of all, it's a product. And when we think acid and base reaction, the acid and the base are usually reactants, not products. The second thing that's going against it is that OH group there usually indicates a base, not an acid. So remember, under our Bronsted definitions, we're talking about acids giving up H plus and bases as taking H pluses. So where we need to go is we need to follow the hydrogen. Where is the hydrogen going? And so if we break ammonium hydroxide into its components, the ammonium ion and the hydroxide ion, it's pretty easy to see that the ammonia, NH3, is what has gained the H plus. That means the ammonia is a base. And if we look closely, the water and the hydroxide are related to each other as well. And we see that the hydroxide is at H plus away from being water. So that means that the water had to have given up that H plus. That makes it an acid. So when we are identifying acids and bases based on reaction and reactivity, that's what we need to do. We need to follow the hydrogen. What is the hydrogen doing? Who's gaining hydrogen? Who's losing hydrogen? And if we can do that, we should keep it straight in terms of what's an acid and what is a base. Now let's move into a slightly different area. We've talked a lot on Wednesday about the idea of electrolytes. And now we can actually fully classify electrolytes as either being strong or weak. Strong electrolytes, we said, dissociate in water. They break apart. That's why they conduct electricity. But now we can actually talk about what kinds of substances do that. And in particular, we're talking about things that are ionic compounds. If an ionic compound is soluble in water, it is going to be a strong electrolyte. Because when it dissolves, it breaks apart completely. We also gave particular examples on Wednesday about strong bases and strong acids and how those break apart completely as well. So when we talk about strong electrolytes, we're talking about 100% ionization. We're talking about full splitting. For the things that don't fully split, we have a subcategory here, the weak electrolyte. These are substances that do conduct electricity when dissolved in water, but they do so at a much lower conversion rate. And because of that low conversion rate, we see a lower conductivity as a result. In this category are really two types of substances. The ones that have partial conversion. Again, usually that conversion is less than 5%. These are your weak acids and your weak bases. So again, how do I tell a strong acid from a weak acid, a strong base from a weak base? Well, unfortunately, it largely is memorization. There are only 6 strong acids. If an acid is not one of those 6, it's weak. The strong bases can all be found in the first 2 groups of the periodic table. If they are hydroxides of any of the alkali metals, if they are hydroxides of any of the alkaline earth metals, starting with calcium and going down, they're strong bases. Everything that's not one of those, but identifies as a base, either by reactivity or by compound formula, it's a weak base. And it would be a weak electrolyte as a result. We can now finally talk about that third category, the non-electrolytes, the substances that don't conduct electricity at all. Now, what's important about these is that we have to recognize that these substances can still dissolve in water. But because of their molecular structure, they don't form ions when they do. Water just interacts with them in a polar to polar kind of fashion. It doesn't interact with them and pull them apart to create ions like it does an acid or like it does a base. So what we usually see here are molecular compounds. And if we look closely at the chemical formulas of those molecular compounds, we will usually find that they are carbon, hydrogen, and oxygen based. They're usually organic in some kind of form or fashion. We're talking about carbohydrate molecules like sugars. We're talking about alcohols. If it doesn't fall into that kind of a category, it's usually either not soluble or it's falling into one of the acid-base categories kind of on its own. So that covers electrolytic behavior kind of broadly. What about ionic compounds, though? We've kind of talked about them as this blanket statement. Well, we know what an ionic compound looks like. We should have at least some idea of how to name those ionic compounds. But how do I know if they actually dissolve in water or not? That's where solubility rules come into play. Solubility rules are guidelines that we attach to ionic compounds to help us put them into a category that is either dissolves in water or does not dissolve in water. And for the ones that dissolve in water, we know that they are going to be strong electrolytes. For the ones that don't dissolve in water, we know that there aren't going to be electrolytes at all because they don't even dissolve into the solution in the first place. So the solubility rules fall into basically three types of categories, starting with the stuff that's always soluble. If you have an ionic compound that contains an ion off of this list, that compound will dissolve in water. What we are talking about here are nitrates. So silver nitrate, sodium nitrate, potassium nitrate, iron 3 nitrate. All of those are going to dissolve in water because the nitrate ion is soluble. Also in here are acetates. Again, same thing. Lead 2 acetate, lead 4 acetate, tin 2 acetate, calcium acetate, piccan acetate. It dissolves. Now, one thing with these solubility rules that we have to be careful of, the rules that we are applying here are different from what we were just saying about acids and bases. So we know that hydrogen with acetate, acetic acid, we know it dissolves in water. But if we're evaluating its electrolytic behavior, it's not an ionic compound. It's an acid. Acids and their solubility, acids and their electrolytic behavior are their own category. So when we are evaluating whether something is a strong electrolyte or a weak electrolyte or a non-electrolyte, the first thing that we always have to do is classify it. Is it an acid? Is it a base? Or is it a salt, an ionic compound? From there, then we can get into each kind of subcategory. If it's an acid, is it strong or weak? That is what affects its solubility, or not, excuse me. That's what affects its electrolytic behavior. Base. Electrolytic behavior is based on whether it's strong or it's weak. Salt. Is it soluble or insoluble? That's what determines whether it's going to be an electrolyte or not. So we have to be careful about that because it's very easy to get these categories kind of crossed up and confused. I'll see it brought up, especially as we get to the solubility rules proficiency, where someone will say, well, hold on. Acetic acid is soluble. It's a soluble salt. It's not. It's an acid, and it needs to be classified as an acid. So there is going to be some crossover, especially with the bases. Because with the bases, when we get to hydroxide salts, a lot of hydroxide salts are not very soluble at all. But when we're evaluating their basic character, we have to talk about their ability to dissociate in water when it does dissolve. That's when we get into strong versus weak. So on this list again, nitrates, acetates, all of your alkali metals. So lithium, sodium, sodium, potassium, rubidium, and so on. The ammonium ion, NH4+, and your chlorates and perchlorates. If you have an ionic compound with one of these ions in it, it will dissolve in water. And remember, if it dissolves in water, we're going to get a strong electrolyte as a result. So that's the first category. Middle category, these are ions that are usually soluble. Now, in both of the next categories, we're going to see this word usually. And what that means is that basically, as a blanket rule, we can expect them to behave according to their category. But there are exceptions. So in particular, with our chlorides, bromides, and iodides, so our heavy, non-metallic halide ions, they will dissolve in water. But there are three exceptions. There's the mercury 1, there's the lead 2, and there's the silver. I'm going to hop in the Wayback Machine here just for a second. I'm going to give you an acronym, a way of remembering this that I was taught when I took chemistry for the very first time. The Chloride Rule: chlorides are usually soluble except for Merle's chlorides. Merle's chlorides include mercury, lead, and silver. So if I have a chloride, a bromide, or an iodide, it will dissolve in water unless it's one of Merle's. If it's one of Merle's chlorides, it's going to stay undissolved. The other ion that falls into this category are the sulfates. Sulfates are usually soluble in water. In fact, sulfates are one of the common vehicles next to nitrates and acetates for getting stuff, especially transition metal stuff, to dissolve in water. There are exceptions here as well. We call them the Balcomer sulfates. And the Balcomer is coming from barium, lead, calcium, mercury 1, and strontium. So if you notice, mercury 1 and lead are exceptions in both of these groups. Mercury 1 and lead have some kind of unique chemistries when it comes to their solubilities. And so they're in both sets of exceptions. So that is the group of ions that are usually soluble. The last group here is kind of a catch-all. These are the ions that are usually insoluble. So in this list, we have a group of ions and then a kind of a catch-all statement at the end. So for example, sulfides. Sulfides are usually insoluble. Sulfides are actually a great way to precipitate out a lot of different kinds of metal ions. The ones that it doesn't work on, ammonium sulfide is soluble, alkali metals are soluble, alkaline earth metals are soluble. Same thing is true for hydroxides. Most of the time, hydroxides are insoluble, which is one of the reasons why it's really hard to make a base out of a transition metal hydroxide. Doesn't dissolve particularly well. When you can get what little that you can dissolve, it acts as a weak base anyway, so it doesn't really move the pH all that much. Exceptions there are exactly the same, which work really, really well in this case because we know our strong bases are derived from alkali metals, from alkaline earth metals. And so if we couldn't get those solids to dissolve in the first place, there's no way we could call them strong bases. The other ions on this list fall into a generic kind of category. They're only soluble with ammonium and the alkali metals, which, if you remember back to the first group, ammonium ion and the alkali metal ions were in the group of always solubles as well. So really, the exceptions here, if you want to think about them, are sulfides with alkaline earth metals and hydroxides with ammonium. Or, excuse me, I misspoke there. Those two in orange are the only exceptions, really. Because if we think about that first group as kind of being primary among all of them, the only true exceptions, alkaline earth metals with sulfides, hydroxides with the alkaline earth metals. Everything else can be explained by that always soluble list. And that always soluble list is the primary rule. It is not contradicted. If it has an ion on that list, it's going to dissolve. It doesn't matter what the other ion is. So there you have your solubility rules. Let's do a little bit of practice exercising here before we move on to using the solubility rules for chemical reactions. So what we need to do is we need to put these three compounds into two categories. First of all, we need to identify it as an acid, a base, or a salt, or in this case, it says neither. And we have to classify it as a strong electrolyte, a weak electrolyte, or a non-electrolyte. So we start with sodium chloride. Sodium chloride, we can very clearly see is an ionic compound. How do we recognize it as an ionic compound? Well, we've got a metal and a non-metal. Kind of the easiest way to pick out an ionic compound. And there's no hydrogen, there's no hydroxide, so it can't be an acid, it can't be a base. As an ionic compound, we know it is going to be a strong electrolyte if it dissolves in water. And since sodium is on that list of always solubles, it's going to dissolve in water. For hydrochloric acid, or excuse me, for HCl, we should recognize right away hydrogen ion here, this is an acid. Now we got to go into, is it a strong acid or a weak? Hydrochloric acid is one of the 6 strong acids, so we know it is a strong acid, and so therefore it would be a strong electrolyte. This last one, ethylamine, CH3, CH2, NH2. This one is tough. This is clearly a covalent compound. It's all nonmetals. carbon, hydrogen, and nitrogen. So we might be tempted to put it into that neither category as a non-electrolyte. If you read closely in your book, however, what you will see is that compounds, organic looking compounds with nitrogen in them, the nitrogen actually acts as a Bronsted base. So this is in fact a base. It is not one of our group 1 or group 2 bases, so it is weak. By technical definition, we would call it a weak electrolyte. However, since we are not focusing too much on organic acids and bases, if you had classified this as neither and a non-electrolyte, I wouldn't have held that against you either. But if you're looking in your textbook, you'll see a lot of carbon and hydrogen structures that have a nitrogen group on them somewhere. That nitrogen group is basic. When these substances come into contact with water, they act as Bronsted bases. They take that hydrogen from water and they leave behind a small amount of hydroxide. Now, their strength as bases is lousy. We're talking like pH 8 bases, pH 9 bases, really, really, really weak. Like I said, if we're thinking about it in the larger context of what we're trying to get across to you right now in this course, if you recognize that as a molecular compound and as a non-electrolyte, that's good enough for me right now. I'll let Dr. Peralta fix this little bit for you when you get to organic chemistry, because that's really the only place where it would apply. And since most of you aren't going that far, because you don't have to, we're not going to dwell on any more than what we just said right now. So how do we go about using these reactions? How do we go about using these solubility rules and all of this stuff about electrolytes? Well, the answer to that question is actually posed by another question. If I have a reaction that is taking place in aqueous solution, how do I know it actually happened? Because we know there are some occasions where it's very clear that something has occurred. I put one solution together with another and a gas forms. Well, clearly something happened to give us the gas. I put the two solutions together and I get a solid. Clearly something happened to give me the solid. But what if I put solution 1 and solution 2 together and I see no color changes, no solids, no gases? It looks exactly as it did before. Does that mean that nothing happened? Not necessarily. If I give you a double replacement reaction, does that actually mean that the reaction occurred the way that it says in the equation? We don't know. We wouldn't know until we actually tried it. And so what we have to look into there are a couple of kinds of reactions that we do know, and there is a technique that we can use to help us to frame whether or not something is a reaction or if something is a solution. Because if I mix solution 1 and solution 2 and nothing happens, then there was no reaction. We just made a more complicated solution. So let's take a look at those precipitation reactions first. A precipitate, by definition, is a solid product that comes from the formation of a reaction in solution. I put solution 1 and solution 2 together, a solid falls out of that solution. That solid is called a precipitate. Now, if we don't do the reactions themselves, we can still predict precipitation using our solubility rules. Because our solubility rules would tell us, okay, that compound should be soluble, that compound should be soluble, this one should be insoluble. That must be the precipitate. Acid-base reactions are a little bit more difficult. Again, if I'm just giving you two solutions and I'm not telling you what they are, an acid-base reaction would show no visible sign of reaction. It was clear and colorless to begin and clear and colorless at the end. But from a chemical reaction standpoint, I can usually determine an acid-base reaction because I can see an acid and a base based upon their chemical formula as the reactants, and water and some kind of ionic compound as the products. And since water and an ionic compound are the products, that's often the reason why we can't see the reaction. Water is clear and colorless, just like the acid base were. And if that compound that they form dissolves in water, we have no evidence visually to conclude that a reaction occurred. But luckily, we do have a way of promoting a means of showing and proving that reactions are actually taking place. We call those ionic equations. Now, ionic equations are adaptations of molecular equations. Thus far, everything we've given you has been a molecular equation. This substance plus this substance gives you products. What an ionic equation does is that when we're doing reactions in solution, it gives us a more accurate picture of what is actually happening. Because when we know that when we have stuff that's in solution, it doesn't actually appear in its molecular form. If it's electrolytic, we know it's going to split into ions. The ionic equation shows us those ions and shows us how those ions are rearranging themselves, how they're reconfiguring themselves to get us to the products. Using ionic equations, we have a definitive way of seeing if a chemical process has occurred. Because if a chemical change has occurred, we will notice a difference between the reactants and the products. In some kind of way, we will have gone from ions on one side to something that's non-ionic on the other. Or maybe it's the opposite. We start with something that's non-ionic and show it splitting apart. Regardless of what the conditions are, an ionic equation allows us to show that change. And if for some reason there isn't any change, the products look exactly the same as the reactants, well, that's useful information as well. That tells us that a chemical reaction didn't occur. Instead, we've just created a more complicated solution. Now, the process of converting a molecular equation to an ionic equation is a little bit difficult. Not because the individual processes are difficult, but because you are integrating several concepts at the same time. So we're starting with something we know, the molecular equation. Below it, we're also doing something that we should have at least some familiarity with if we understand the solubility rules. And that is breaking it apart into categories. This substance is a weak acid. This substance is a soluble salt. this substance is a strong base. Identification. That's all that the second step is. The third and fourth steps are where it can get complicated for us. Because what we have to do is we take those classifications, and if it is a strong electrolyte, so if it is a soluble salt, if it is a strong acid, if it is a strong base, then we show that by taking whatever the molecular substance was and breaking it apart into its ions. If it's not a strong electrolyte, if it is a weak electrolyte, like a weak base, like a weak acid, like an insoluble substance, whether it be a solid or a gas or a pure liquid, it doesn't ionize. It stays the same. Keep it in molecular form. And then the last thing that we do, and this is what allows us to determine if the reaction has occurred or if it has not, is we start to look for spectator ions. Ionic substances that are the same on both sides. So I had sodium ion on this side, I had sodium ion on this side. Obviously, the sodium ion did not participate in any kind of chemical reaction. It just was there as a vehicle to get whatever it was in the solution. So as a non-participant in the reaction, we call it a spectator ion. The goal of a net ionic equation is to remove all the spectator ions. And whatever's left over after we do that, that's our net ionic equation. That is what tells us if the reaction occurred or if it did not occur. And so from that, we can look at our net ionic equation, and if there's still something there, then we know that we had a chemical reaction occur. We have evidence of that reaction. If everything crosses out and there's nothing left over for the net ionic, then we know that a reaction did not occur, and we have the evidence now to prove it.